Hey YouTube, hey YouTube. Today, we're studying gravitational fields or gravitation. So this is kind of a lengthy topic. So I've divided it into four parts. The first part being universal gravitation, which is mostly theoretical. The second part being gravitational fields, gravitational, then gravitational potential, and so on. So, right now we're gonna do our first video on universal gravitation. Also, if some of you want notes, I have colorful notes, and just leave a comment, and I'll try to email them to you. And I do check my YouTube every 2 or 3 hours, so you shouldn't wait that long. Anyways, universal gravitation. So basically, every set of two masses exerts a force on each other, which is gravitational force, and gravity is an attractive force. So both of these masses, they naturally tend to want to attract each other and get together, right? There are a lot of forces stopping them and so on, and we're going to study about them later. So first of all, gravity is not a derived force or something caused by something else. It is one of the fundamental forces, which are basically unexplained forces. You don't know where they came from, but they do exist. Other forces like these include uh, nuclear strong force and so on. I haven't really revised them, so I don't know them that well right now. But moving on, the first thing we're going to study is Newton's law of universal gravitation. So, Newton's law of universal gravitation, it states that uh, whenever two point masses exist, they exert a force on each other, and the force that these two bodies exert on each other is directly proportional to the square of, not the square, the product of their masses. So let's say this marker here is m1 and this marker here is m2. So the force that this one exerts on this one and the force that this one exerts on this one is equal to, directly proportional to, this mass m1 multiplied by m2. All right. Also, this force is inversely proportional to the square of the distance between them. So let's say um, there's a distance of r between these two. So the force that this marker exerts on this marker and vice versa would be inversely proportional to r square. And I hope all of you know how proportions work. So we can simplify this proportion by writing it as force is directly proportional to m1 multiplied by m2 upon r squared, right? um, yeah, like this. And then whenever we remove the proportion sign, we have to add a constant, f equals to k m1 m2 upon r square. And this k here is replaced by a capital G, g m1 m2 upon r square f. Now this g here, you see, is a universal gravitation constant. So its value is 6.67 exponential minus 11. And exponential means 10 to the power minus 11. So yeah, that's it. And its unit is Newton meter square kg minus squared. I'll just write it down here. 6.67 into 10 exponential minus 11 Newton meter square kg minus 2. So if you guys want to know what this means. I don't really know it myself, but if you maybe give me a minute, I can do it for you. Okay. What does universal gravitation constant mean? Hmm. So Google says it's a constant, which is what I said. Let's see. Okay, so this constant has a deep meaning. You need a deep understanding of physics for that, so I'm gonna skip it because even I don't get it. Anyways, moving on. So we were discussing the formula for gravitational force, which is Gm1m, which is Gm1m2 r square, and no matter how big or small the masses are, uh, there could be this mass and there could be this mass, but the force that they exert on each other has to be equal always because of Newton's third law, which is every force has an equal and opposite reaction. Okay, so moving on, an object's weight depends upon its altitude. All right, so this gravitational force, which you calculated, Gm1m2 upon r square, it is a force, yes. So that's why we can also call it an object's weight when referring to a planet. So basically, an object's weight depends upon its altitude from the surface of the planet and the mass of this object. Because the mass of the planet is going to be constant, it's always going to be dependent on that. Anyways, so the greater the mass, the more the weight, the lower the distance, the altitude from the surface, the more the weight. And we have several examples of, or actually proofs of gravity existing, which is pretty dumb because we do know it exists, and we also know that the earth is spherical and not flat, but that is a debate for some other day. Okay, so the first and most obvious example is the orbital motion that all interstellar bodies show. Is show the right word? That all interstellar bodies feel, whatever. And we know it exists because you see, an object was moving in this direction, but this planet over here, it attracted this object towards it. So it's not going to just like that. It also has a tangential velocity towards this direction. So it's just slowly going to start curving and then start orbiting this planet. And it might slowly get closer and closer, but it's going to take a long time because there are no frictional forces, restrictive forces on in space because it's a vacuum. So there's nothing stopping this speed, slowing down the tangential velocity. And when the tangential velocity is not going to slow down, it's not going to decrease, it's not going to start moving towards the center, it's just going to start keep on orbiting at the same radius. Okay, the next example includes the formation of stars. So you see, how stars are formed is that there's one atom and then there's another atom, and of course these atoms do exert a force on each other, but they also have a high kinetic energy. But also there is nothing else in the entire space at that given point, so they have no other choice than to just keep on moving but also staying close to each other. So these are close to each other, and then They keep on floating through the universe, and then they meet another pair of particles, atoms that are also sticking close to each other. And you should know that these are hydrogen, because hydrogen and pieces of dirt, because that's all that mostly exists in the universe, and that is what stars are made of. So these four join together and they make up a kind of a bigger cluster of atoms, and then this cluster of atoms finds another cluster of atoms and they join together to form a bigger cluster of atoms, and they keep on joining, they keep on getting bigger, and at one point they're big enough that they can hold themselves in. There's no uh, protective shield holding them in, it's just gravity, and they have high temperatures, billions of degrees Celsius, but they still are able to stick together despite that high kinetic energy, and that is all due to gravity. There are like trillions and trillions of atoms attracting one atom, and then the same number of atoms attracting one other atoms. The proportions are high, and that's why they stick together. Okay, moving on, we have the example of spacewalks, which is um, when astronauts exit their space shuttles in vacuums in zero gravity. They are tied together with the spaceship, but they seem to be traveling parallel to it. But what's happening is that slowly, and this was checked, it was simulated through computers over millions of years. What was happening was that they were slowly they were trying to get together, like they weren't getting together, but their paths were not parallel, they were slowly colliding, they were, what do you call it, intersecting paths. So we can see that even though the gravitational attraction was weak, but it did exist. So there we have another proof, and then another proof, the final proof, which 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 I can explain staying within the bounds of our syllabus, even though there are billions and billions of proofs. Uh, Last proof is that objects around us are unable to attract each other, and that may sound a weird example, a weird proof, because that is the entire opposite of what we're saying here. We're saying that all objects exert a force, but then why doesn't an ant get attracted to us? Because we are significantly a lot of times bigger. So that's because the gravitational acceleration, the gravitational attractive forces of that ant are so insignificant, because as we know, it depends upon the mass. So the mass is so significantly small that multiplied by the gravitational potential constant, which is even a smaller quantity, exponential minus 11, it's so small that the frictional forces on that ant, on that object, are still way bigger than the attractive forces, and that's why they stay at one point. You see, that's it. So, that was the beginning of gravitation, and I know it was pretty useless because you guys are not here for theories, you're here for explanations for the harder parts, but I did had to start somewhere. I hope you guys enjoyed, and now I'm gonna go and make the video for the second part, the gravitational fields. If you need notes, if you need help, if there's some questions, I'm always here. You can comment, you can message me, you can email me. I guess emails are available on YouTube, or just message me. I'll reply within 6 hours max. So that's it. Hope you enjoyed. Stay tuned.